Now, today we've got two significant proofs. So we're going to have to just jump right into it. We know the definition of compact. I'll just repeat it real quick. Compact, it's a property of a set in a metric space, and it says that every cover admits a finite subcover. Oops, and forgot a very important word there. Every open cover admits a finite subcover. I see Alexis's question there. Do I suggest you do all the problems in the lecture notes? Yeah, although I think there was one of them from last time, as Daniel clarified this morning, that needs something from today's lecture. So you should try all the problems, but every once in a while I'm going to make a mistake and put something there that you can't do yet. Okay. As far as the problems from the book, I haven't even looked at those yet. I will, and then I'll let you know. Okay, so that's compactness. Now we want to prove some theorems about this. And by the end of today's lecture, we're going to know exactly what the compact subsets of the real numbers are. We're going to have an exact characterization of what compactness means there. So here's our first theorem. And this is the biggest proof we've got today. All closed and bounded intervals are compact. Okay. Remember, there's several forms of closed intervals, but once we say closed and bounded, it really is that standard closed interval you're used to. Okay, so let's just jump into the proof. Let's take one of those guys. So it would be a closed interval from A to B. Be a given closed bounded interval. We can always assume A is at most B. Otherwise, the set would be empty. A might be equal to B, but now let's take an open cover. Okay, so we get a bunch of open sets. The union contains this closed and bounded interval. We need to find a finite subfamily of that open cover that still covers the interval. Now, we're going to start with a really trivial point, but it comes up a few times. The point A is in this interval. So there must be a set that has A. And I will call that set U sub A. Okay, now we're going to dispense with the stupid case where A equals B. It's done, right? So if we did have the endpoints equal, then just that single set by itself would be our finite subcover. because in that case, the interval would just be the point A. Okay, so now we can assume that B is greater than A. Okay, so we have more than one point in our interval. And here is where the proof gets a little bit sneaky. We're going to define the set. Well, how about I just write it? The set of all points x in our interval Okay. So these are the possible right-hand endpoints where we could stop and we would have a finite subcover. Now, we want to argue that S is actually the entire interval A to B, because we would like the closed interval from A to B to itself have a finite subcover. Okay, so how are we going to get there? Well, first of all, let's notice that S is an interval. Okay, think back to last semester. What does it mean to be an interval? It means you satisfy the betweenness property. So let's just check that real quick. If x is less than or equal to y is less than or equal to z, where x and z are in this set, then y is in this set. Well, if z is in that set, then you can cover, the closed interval from A to Z has a finite subcover. Well, so the closed interval from A to Y also has a finite subcover. It has the same finite subcover as the closed interval from A to Z. Is that okay? So, remember, we want S to be the whole interval from A to B. Now we know it's an interval. We're going to argue about its subprimum, but first we have to know that it has a subprimum. So is it non-empty?
Yes, because we have an A in it.
Yes. Okay, this goes back to the beginning of the proof. where we said there is some set containing A. S is non-empty. Okay. So what do you need to be to have a supremum?
You have to be you have to be bounded from above and be non-empty.
Mm-hmm. And so is S bounded above?
Yes, it's bounded by B.
Mm-hmm. By its very definition, S is a subset of the interval from A to B. I'll save a word and just write bounded, but we care about bounded above. But that shows that it's bounded on both sides. Okay, so therefore it has a supremum. Okay. Now, that's from the supremum property. Maybe I should definitely write that. This is by the supremum property. Of the reals. Okay. Now, just while we're on this topic, remember, the supremum property, we didn't prove it. Okay. It's an axiom of the real numbers that we just accepted last semester. Now, we used the supremum property to prove completeness. Everybody remember that? So really, we're using the completeness of the real numbers here. This proof wouldn't necessarily work if our metric space was the rationals with the same metric. Okay? That said, the result is still true for the rationals, but it's true for you need a kind of sneaky proof. Okay, this proof right here is literally, it wouldn't hold for the rationals. Okay, so we know that the supremum of S, we know it exists. We know that it's at most B. That's because B is an upper bound on S. Okay. And we know that the supremum of S is strictly greater than A. I'll just write the reasoning for the strictly greater here over on the side. Okay, so remember we already said there's a set in our cover, in our open cover that contains A. That set's open, so it contains a neighborhood of A. Therefore, that set contains numbers that are larger than A. Well, any other number that's in that one open set is also in S because we have a finite subcover going up to that number. Okay. So, we're good so far that we got a supremum. And we know it's somewhere between A and B, but it's not A. It's larger than A. Okay. Let's move on. There's another set in our cover that contains the supremum itself, because the supremum is in our interval and our cover covers our interval. So there is some set, we'll call it U sub S, okay. Now, that's an open set, so we have a neighborhood of S. So I'm going to combine two things, and then we'll just check that it works. Okay. Here are the two things I want. So what I've said here is I want the supremum of S minus epsilon to still be bigger than A. Well, I know the supremum of S, we know it's strictly bigger than A, so there is some epsilon that we could take off another epsilon and still be bigger than A. And at the same time, we want an epsilon.
Daddy,
We want an epsilon. Can you wait? We want an epsilon so that the epsilon neighborhood of the supremum is in that set U sub S. Well, U sub S is open, so there is some epsilon that does that. Well, since I know I can do both of these with some epsilon, I take the smaller of the two values, and it does both. Oh, good. Okay, so there's some epsilon that does both. This is our standard, if we wrote it out, gave them both Greek letters, then we'd take the minimum here. We okay so far? Okay, so let me maybe draw a picture over here. Here's A, here's S. We're going to take a little neighborhood. There we go. That's, well, sorry, S, I'm calling it supremum. That's the epsilon neighborhood, and then what is US contains that. I don't know where. That's U sub S. Okay. Now.
I have a question.
Yes.
On the first line there, we say sup S is less than or equal to B, right? So if it were equal, then would you have like this neighborhood around it, and then therefore would you have this U sub S set?
Mm-hmm. Yeah, it's interesting. So that occurred to me while I was writing this proof, and So you have to keep in mind that the sets come from the real numbers. The cover is in the metric space, so the cover is in the reals. So the cover covers to the right of B. It has to, just like it has to cover to the left of A. But to the right of B. I mean, there's some set in the cover that contains B, and so it contains a neighborhood of B. So the cover has to extend to the right. Okay, it can't just cut off at B.
Okay, cool. That makes sense. Thank you.
Yeah, Benjamin sees where we're going. We want to take a finite cover that we already know and add this U sub S to it and push farther to the right. But here's the problem. We don't know that we can cover up to supremum. We know that it's the supremum of the places we can cover up to, but we don't know that we can actually cover up to the supremum. So we have to be a little careful. Okay, so there must be some point T in our set S with. Okay, go back to our picture. Remember, that's the epsilon neighborhood. I'm going to go there. That number would be supremum of S minus epsilon over 2. There must be some point in our set that's bigger than that. And that's what T is going to be. Okay, there must be some point in our set that's bigger than that because the supremum is what it is. It's not any smaller. Okay, so what do I want that point to do? Okay. So really what I'm saying is I want that point to be larger than supremum minus epsilon over 2. And I can do that because the supremum is the supremum. And then, of course, it's going to be at most the supremum. And we already said that the supremum minus epsilon over 2 is greater than A. Okay? Now, by the definition of capital S, we're going to use our finite subcover up to T. Now, V covers A up to T, and our U sub S set overlaps with it. It actually goes down lower than T, and then it covers all the way up to, well, past the supremum. It doesn't cover necessarily the supremum plus epsilon, but it covers the supremum plus epsilon over 2. A lot of U's in that statement.
Can you repeat the reasoning for that?
The reason why we cover all that? Sure. V covers from A to T. Okay? And the set U sub S contains the epsilon neighborhood of the supremum. So that will take us up to, well, up to at least supremum plus epsilon over 2. The reason I'm not writing plus epsilon right there is because I don't know that the closed interval up to epsilon is going to be covered. Okay.
So V covers up to T.
Mm-hmm. This part is our
because
finite
of-
subcover of A to T.
Okay, so how do we know that it covers beyond T again?
Well, that's the U sub S set.
U sub S, okay.
That one by itself covers T up to the supremum plus epsilon over 2.
Okay, that makes sense. Thank you.
Mm-hmm. Well, this is a contradiction unless it's a contradiction to our definition of supremum unless the supremum of S equals B. And in that case, if the supremum of S is equal to B, then what we've just constructed is a finite subcover of the whole interval.
Excuse me, why did you have to use epsilon over 2 instead of epsilon? Because didn't we say that the supremum plus epsilon is contained in U of S?
No. This is really it's because we're talking about an open neighborhood there.
Mm-hmm.
So actually, the supremum plus epsilon doesn't need to be contained in U of S.
Supremum plus, but that's a subset of U of S, right? That interval?
This open interval is a subset.
Oh, the open interval, right? It's
Yeah.
open. I wasn't thinking about that. Okay.
Yeah, so that's why the epsilon over 2's have to come in.
Yeah, that's fine.
And this whole reason that we have to go back to supremum of S minus epsilon over 2 is also because we don't know that the supremum itself is a member of the set, so we don't know that we can cover up to the supremum. So we have to go back epsilon over 2 to sort of link up our covers.
I have one more question. Can you clarify why is there's a contradiction if the supremum is less than B?
If the supremum were less than B, then we would have found that that we can actually cover that closed interval. So we would have found that that's in the set. Well, that's bigger than the supremum. And you shouldn't have anything bigger than your supremum in your set.
Okay. So if the supremum is B, so and something bigger than B is then that, right? Like if a supremum is B, then B epsilon over 2 is in S.
Well, okay, so. Oh, I'm sorry. It's not actually a contradiction. I need to explain this better, okay? There's actually no contradiction here. Here's the point. What we've said is that we can cover up to that, right? So now, here's the thing. If supremum of S plus epsilon over 2 is less than or equal to B, then the supremum of S plus epsilon over 2 is in S. Now this can't be. In fact, sorry, I can say that even better. If the supremum of S is less than B, then we can find something larger. S contains something larger than it. And that can't be, because you can't contain, a set can't contain anything larger than a supremum by just definition.
Sorry, I'm still not clear why it cannot contain something larger than B if the supremum is less. Like, I get that S can't have anything larger than B.
Larger than, oh, yeah, okay.
But why does S have something larger than the supremum if supremum is less than B?
Because we've shown that we can cover the closed interval from A to the supremum of S plus epsilon over 2. Okay. The definition of S was all the numbers X so that we could cover the closed interval from A to X.
Oh, okay. Okay.
So T is just this is the standard supremum kind of argument. We'd like to talk about supremum of S minus epsilon over 2. But that doesn't really need to be in the set, so we talk about T. T is just, we're using the supremum property. Anything smaller than supremum, then there's something in the set that's larger than that. Okay. Let's move on. Oh, so what did we prove? We proved in the real numbers with the standard metric, closed and bounded intervals are compact. Now, we're going to strengthen that quite a bit. And we're going to strengthen it by actually this pretty easy, well, I mean, compared to what we've just done, this pretty easy result. And this result holds generally. Oh, so before we get to this result, let me just point out, let me ask this question. This was all very much in the real line. Okay. What would you expect this to look like for arbitrary metric spaces? What would you expect this result to look like?
Well, we rather depended on the completeness of the real numbers. So I suppose we could extend this to any complete metric space, so to speak.
Mm.
Yeah, a little bit.
There's something else that we depended on even more than completeness. And I don't mean supreme.
Closedness?
What's that?
Closedness?
Well, closedness isn't a problem. So the statement of the theorem uses intervals. What does an interval look like in a general metric space? Oh. Yeah, okay, that's a pretty good answer. Yeah, okay. Sorry, yeah, that's a good answer. Uh-huh. Okay, cool. So in a general metric space, we might expect something involving balls, finite diameter, Christian says. We might expect to need completeness because we used completeness in the proof. Okay? So let's keep that in mind, and we're going to prove this result, which is pretty powerful and pretty easy to prove. The last one is kind of pain. This one is not. So in every metric space, it doesn't matter where you are, every closed subset of a compact set is compact. So once you know you're in a compact set, if you're closed, you're compact. Okay. Let's prove it. So let XD be a metric space. And let's let K be compact. And I want to be clear that's compact in whatever space we're in. Okay, and then let's take a closed set C inside K. And I want to be clear, I don't mean, I'm going to write that it's closed in XD. That should be what you understand by default from that statement, but I don't want you to get it confused with like being relatively closed in K. That's not what we're talking about, okay? It's just closed in the space. closed in the big space. Okay. Now we want to prove that C is compact, so we're going to start with an open cover. Let U be an open cover of C. Okay. Now, what do we have to use? We have two hypotheses. One is that C is closed. The other one is that K is compact. If we're going to use the fact that K is compact, we're going to have to get an open cover of K. Okay, because you can't use that hypothesis unless you have an open cover. So if you think about it, somehow we have to convert this open cover of C into an open cover of K. Any idea how to get an open cover of K out of this thing? Well, oh, Benjamin?
Oh, I was gonna say, I mean, because we could consider, we could take C out of K minus C, and then consider the rest of K, what's left over, and then find an open cover of that. And we know that since, so we could do it that way. We could just consider K minus C.
Yeah, but we don't know that K minus C is compact.
Oh, true.
Yeah, so we don't know that compactness is preserved by any nice things. And it's not. I mean, it's not like we don't know for a good reason. It's because these things aren't preserved by that kind of stuff. Oh, here's the thing. C is closed. What does that mean? What should pop into your head about a closed set?
Its complement is open.
Yeah. Now, what if I add its complement to U? What does that cover? Yeah, Roger has it. It covers X. And we don't even care about that. And in particular, it covers K. Okay. Now I'm going to have to run through the end of this proof because we're running low on time. But because now we got to cover a K, we've got a finite subcover. So there is a finite subcover. Oops. But I want to... We did this last time too. I'm going to be a little bit tricky about how I define it. I'm going to take a subfamily V of U such that V together with X minus C covers K. That's the compactness of K. And now clearly we don't need the complement of C to cover C. So V itself covers C. Okay, we took an open cover. We found a finite subcover.
I'm still a little confused on why V covers C. So I see we have this. Oh, because V is a subset of U and U covers C,
Yeah.
right?
Well,
Well, no.
no.
Right.
V together with the complement of C covers K.
Right.
Well, you're not going to need the complement of C to cover C, are you?
Well, how do we know that any cover of K is gonna cover C because C is a subset?
Uh-huh. Yeah,
Okay.
C is in K. Yep. And you definitely don't need you don't need the complement of C in order to cover it.
Okay, I see. Right, because none of those points are in C.
Yep.
Okay, that makes sense.
Good. Now, what can you do with the two results of today? You've got, the first one said every closed and bounded interval of the reals is compact. The second one said any closed subset of a compact set is compact. So now what happens when you combine them? Okay, well, any closed subset of a closed and bounded interval will now be compact. Okay? Because it's a closed subset of what we proved in the first result to be a compact set. Okay, but we can write that a little bit better. A closed subset of a closed and bounded interval. Well, to be a subset of a closed and bounded interval, there's a much easier way to say that. Okay, the much easier way to say that is just bounded. If you're a bounded set on the real line, you're contained in some, our definition says you're contained in some interval, but just expand the interval to include the endpoints. Now you're contained in some closed and bounded interval. That closed and bounded interval is compact. You're now a closed subset, blah, blah, blah. So any closed and bounded set in RD is compact.
How do we get that from the theorem? We just showed that closed intervals are compact, and we only showed that closed subsets are compact. So how come open intervals on the inside are compact?
Oops, I'll use blue. Let me just sketch the proof. We're out of time,
Oh, wait,
but
why
I'll
am I even
sketch the
talking about
proof.
open? You wrote closed. Forget what I just said.
There is some. Right? Bounded means that. So you get your closed and bounded compact set that you're a subset of just from bounded. Okay, so we ran a couple minutes over. Let me stop the lecture now.